So in this session we will discuss numericals on thermal stresses. And to solve these numericals, in the earlier lecture we seen concept of thermal stress and strain, where we know that when material is heated by temperature T, delta T of length L and coefficient of thermal expansion alpha, then change in length of the material is given by alpha L delta T. And we seen thermal strain induced in that material due to this change in length prevented is equal to alpha L delta T upon L if length is totally prevented, and is equal to alpha L delta T minus gap upon L if it is partially prevented. Based on this, we know that stress is equal to E, that is modulus of elasticity, into thermal strain, and from this stress formula, that is thermal stress, we can determine support reaction exerted by support on that material. So let's start with one simple numerical. So this is our statement of the numerical. We have to use these formulas. So statement is, we will write some given data based on this. What is given? A steel bar of 40 mm diameter and 5 meter long. So some dimensions are given that we will write here. Diameter of the bar is 40 mm and it is 5 meter long. Length of the bar is 5 meter and it is heated to a 60 degrees Celsius. So temperature is increased by 60 degrees Celsius. So delta T is equal to 60 degrees Celsius with its ends clamp before heating. Calculate thrust exerted by the bar on the clamp. So what is given? A bar is given like this. Its ends are clamped at both ends and now it is subjected to heat, that is delta T. This is your statement. So they ask you calculate thrust exerted by the bar on the clamp. So we have to find out how much thrust, or you can say force, exerted by these clamps, the supports on this bar. Let's say that force is F. But we have to find out in two cases. Case 1, when clamps don't yield, and second case, when one clamp yield by 0.5 mm. So case 1, clamps don't yield means what? It is completely prevented. So this support does not yield, it will remain same. So it is your case 1. So when expansion is totally prevented, there is no yielding. And they ask you case 2, when one clamp yield by 0.5 mm. So this is your case 1. This is your case 1. There is no change in support. And case 2 is like this. This is your support here. This is your bar. What happened? One clamp yield by 0.5 mm. So initially the support is here, but due to heating, one clamp yield by 0.5 mm. Supports get yielded, and this gap is equal to 0.5 mm. So this is your second case. Also, value of E is 200 GPa and alpha is equal to 11 into 10 raised to minus 6 per degree Celsius. So we have to find out force value. So how we can find out? Very simple. We consider case 1. So this is your case 1. So when clamps don't yield, it will remain same. So in this case, we already seen formula for this. See, clamps don't yield means totally prevented. So formula is what? Thermal strain is equal to, we know formula, alpha L delta T upon L. This is your length prevented upon L. As we know all these values, that is alpha is known here, yes. Then L is known and delta T is known. Everything is known. So we can put it here values and we get answer. So if you solve this, your answer is 6.6 into 10 raised to minus 4. As this is strain, we are not writing it's unitless. Okay. So this is your value of thermal strain. Now once we get thermal strain, we know that sigma is equal to, so this is your thermal strain, and we know that sigma that is thermostress is equal to E into ET. So modulus of elasticity is given 200 GPa. So we'll put in 200 into 10 raised to 3 because we are putting in MPa into your ET value. It is 6.6 into 10 raised to minus 4. If we solve this, we get thermostress is equal to 132 Newton per mm square. So we get thermostress. Now how to find force? To find force, we know that sigma is equal to F upon A. Sigma is known 132. That is F is equal to sigma into A. Sigma is 132 Newton per mm square into area. Now area is how much? This bar is given of 40 mm diameter. So this is circular cross section. So it is equal to pi by 4 into d square. Pi by 4 into d square. So it is equal to pi by 4 into 40 square mm. And hence we get F in the first case, it is equal to 165.876 into 10 raised to 3 Newton. This is your force value when expansion is totally prevented or supports don't yield. It will remain same. Now in the case when supports yield, we know formula of ET. So when there is gap given in the problem, very simple, ET is equal to alpha L delta T, your allowed expansion minus gap upon original length. So if you put all these values here, alpha is given how much? Alpha is 11 into 10 raised to minus 6 into L. L is 5 meter, we put in mm. So 5 into 10 raised to 3 into delta T is 60 minus gap. Gap is 0.5 mm given. This gap is 0.5 mm. So 0.5 upon L. How much L is again? 5 into 10 raised to 3. So if you put all these values, that is alpha, L, delta T, gap and L, then you get answer of ET as 5.6 into 10 raised to minus 4. So this is your value of ET when supports yield by 0.5 mm. And again similar way here, as we find out in the previous case, we have to find sigma. So sigma is equal to F upon A. Before that we also know that sigma is equal to E into ET. So modulus of elasticity is known. It is given to you. It is 200 into 10 raised to 3 MPa into ET is 5.6 into 10 raised to minus 4. So that we get value of sigma, and the sigma is 112 Newton per mm square. So we get sigma here. Once you know sigma, then we can find force here. So put in this formula. Therefore force is equal to sigma into A. Sigma is 112 into area. In this case also area remains same, that is pi by 4 into d square, because the bar diameter remains same, into pi by 4 into 40 square. So we get F in this case it is equal to 140.743 Newton. So we seen here value of force exerted by supports. In case 1, when supports are not yielded and when supports are yielded are different, in the first case it is 165.876 into 10 raised to 3 Newton, while here it is 140, of course here also 10 raised to 3, 140.743 into 10 raised to 3 Newton. So likewise we solve a numerical on a thermostress in two cases given, when supports are yielded and when supports are not yielded. Very simple, we use strain formula, stress, and then stress formula in terms of force reaction. We will solve one more numerical on the same concept of thermostress and strain. So let's say given data first. A steel rod 20 meter long. So length of the rod is given it is 20 meter. At 20 degrees Celsius, initially T1 is equal to 20 degrees Celsius. Find free expansion of the length when temperature is raised to 65 degrees Celsius. Means T2 is equal to 65 degrees Celsius. And in this case we have to find out, so when for the case let's say for this given, we have to find what? Pre-expansion, that is delta L. In the second case it is given also find temperature stress produced. So we have to find out, in the second case we have to find out sigma T temperature stress produced when rod is permitted to expand only by 5 mm. So we have to find sigma T when permitted expansion is how much? Let's say Y is equal to 5 mm. Value of E is given. E is equal to 200 GPa. Let's say 200 into 10 raised to 3 MPa. That is Newton per mm square. And alpha is equal to 17 into 10 raised to minus 6 per degree Celsius. So let's say first find out this delta L. As we know, that is in solution part. They ask you if it is heated to 65 degrees Celsius. Initially temperature is 20. It is heated to 65 degrees Celsius. How much delta L? Formula for delta L is when free expansion, because they ask you free expansion. So free expansion is equal to alpha L into delta T. So alpha is how much? Alpha is given 17 into 10 raised to minus 6 into length is 20 meter. I put in mm, 20 into 10 raised to 3 into delta T. Now delta T is T2 minus T1. That is 65 minus 20. So if you put this, we get value of delta L, that is free expansion, and this value is 15.3 mm. So we get first answer when there is free expansion. Now consider second case. What they said, it is just like this. Initially rod is like this. It is allowed for free expansion initially. So we find out this, and this free expansion is delta L, that is alpha L delta T, that we find out. Now what they said, also find temperature stress produced when the rod is permitted to expand by 5 mm. Means total expansion how much it is? 15.3. But we are not allowed to expand it by 15.3 mm, but instead of this we allowed only 5 mm expansion. So there is some restriction produced at this end. So instead of delta L, now it is subjected to allowed expansion is only 5 mm. So what happened? This much expansion is restricted. In this case, they ask you find temperature stress. So it is very simple. To find temperature stress, we use thermal strain formula. We know thermal strain is equal to what? Thermal strain is equal to expansion prevented upon original length. Original length is L. Expansion prevented how much? It is, this total is alpha L delta T. You can see here, this one is delta L is total expansion. Allowed expansion is 5 mm. Means prevented is how much? This shaded region. So this prevented expansion prevented is equal to delta L minus gap. That is 15.3 minus how much gap is? 5 mm. Upon 15.3, sorry, upon L. L is how much? 20 meter. So 20 into 10 raised to 3. If we solve this, we get answer of this as 5.15 into 10 raised to minus 4. This is your thermal strain. We have to find out thermal stress. So we know that sigma T is equal to E into epsilon T, that is thermal strain. So modulus of elasticity is given, that is 200. So 200 into 10 raised to 3 into 5.15 into 10 raised to minus 4. Your answer is, thermal stress value is 103 Newton per mm square. So it's very simple. Initially they ask you free expansion, and if there is some restriction prevented, restriction given, that is 5 mm only allowed, then how much thermal strain that you have to find out. As per our basic concept, thermal strain is equal to expansion prevented. Understand this one. How much expansion prevented? allowed is delta L, gap is 5 mm. So this one is restricted expansion, that is delta L minus gap. So we put it here, we get thermostrain, and from stress formula, that is relationship between thermostress and strain, we get value of thermostress. That's what ask is. So this is your numerical on thermostress. We see in two numericals, sample numericals on thermostress and strain concept. We'll continue this topic in next lectures.